Hello and welcome to the last session of Porous Media Tea Time Talks in 2022. Today we are hosting two wonderful and esteemed young Porous Media researchers who are going to talk about fluid-fluid interactions in Porous Media. And our first speaker is Sanchay Mukherjee, who is a PhD student at the Department of Energy and Mineral Engineering at the Pennsylvania State University. He is working under the guidance of Dr. Russell T. Johns. His interest in scientific research has evolved and sustained itself through an array of projects relating to petrophysics, reservoir engineering, and machine learning, in many of which have been published in prestigious journal publications and been presented in international conferences. Today, he is going to give a talk on the role of fluid-fluid in interfacial area in hysteresis for CO2 storage. Thank you, Sanchay, for joining us today, and the floor is yours.
Thank you so much, Mohammed, and the whole Porous Media Tea Time Talks team for inviting me. The topic of my presentation today is role of fluid-fluid interfacial area in hysteresis for CO2 storage. So to give an introduction, the multi-phase flow in porous media has many applications in a variety of spaces, such as the groundwater remediation or fuel cells, enhanced oil recovery, particularly the gas EOR, and recently CO2 storage, which has been receiving significant attention due to the global climate change. Amongst all these processes, they all consist of two or more fluids, and relative permeability is a key property that governs the flow and transport of multiple fluids in porous media. And it is very important to accurately estimate it since it can impact a lot of things like the injectivity of the well, the plume, the shape of the CO2 plume, how far it is going across the well, and the hydrocarbon production, history matching, all these parameters. Thus, it is very important that from both economic and environmental point of view to accurately map the relative permeability. Usually, the relative permeability in porous media is modeled as a function of saturation only. In the figure, the Kr curves follow different paths as the direction of flow changes. However, these maps are only possible for a set of curves when it matches the relative permeability, and they are unable to predict the relative permeabilities well when the physical properties, such as wettabilities, change. There are, however, some problems with these models. First of all, they are dependent on the highlighted tuning parameters, which are represented as a lumped version of too many parameters that affect the relative permeability, such as the pore structure, capillary number, interfacial tension, and others. These models are also path dependent and require phase labeling. Because they are not accurate, these models also have problems like hysteresis and thus convergence errors in reservoir simulations. Recent research has improved on these models to come up with a state function approach. This approach tries to make the relative permeability estimation independent of the flow direction. Corsendy in 2017 showed the 6 state parameters that relative permeability is dependent upon. They are saturation, phase connectivity, fluid-fluid interfacial area, pore topology, wettability, and capillary number. Following this, Purswani et al. In 2020 used the state function approach and showed how relative permeability is dependent on saturation S and connectivity X. They assumed all the other parameters such as pore topology, wettability, capillary number to be constant, and interfacial area was not considered. We could, however, see here when the flow direction changes at the same point of S and X, the relative permeabilities obtained from the pore network model were different for the same saturation and same connectivity. Thus, the saturation and connectivity might not be the only two deciding parameters for relative permeability. Thus, in this study, we will calculate the fluid-fluid interfacial area during the two-phase flow in porous media using pore network models, and then determine the sensitivity of saturation, connectivity, and interfacial area on relative permeability to see does it really affect the relative permeability of fluid flow for the carbon dioxide storage in porous media. We have used pore network modeling simulations in the study. We start with a micro CT scan of Bentheimer sandstone. Then we extract the pore network from the image. Previous studies in interfacial area have evaluated it only for a particular type of pore and throat combination. In this study, we used the code from Walwatney and Blunt, and are represented. The pore structure is represented by multiple types of shapes such as spherical, triangular prism, and cuboids. Once the pore network is made, we give some inputs such as interfacial tension, wettability, fluid parameters, and run flow simulations on it. For this study, the wettability has been taken to be 0 degrees, which is completely water wet, and primary drainage, imbibition, and secondary drainage cycles have been run. The simulations predict the transport properties of porous media as output, some of which are shown on the screen as equilibrium saturations, capillary pressure, relative permeability, fluid phases, pore throat dimensions, half angles, and Euler connectivity recently evaluated by Perswani. From the outputs of the pore network, now we can calculate the fluid-fluid interfacial area. In this study, we calculate both the corner areas and the areas associated with the throats. First, we look at the corner areas or the arc menisci. For this, suppose the pore element is a triangle and we have water in the corners while oil in the centers. If we look at the triangular image, we can calculate the length of the oil-water interface using the relation given here, where r is the radius of curvature and beta is the corner half angle. Once we have the length of the oil-water interface, we can multiply it with the length of the pore element and sum it across the number of sites to get the arc menisci or the corner areas. For the interfaces at the cross sections of pores and throats or main terminal menisci, we can calculate the area from the length of an arc using geometry. In this, the throat areas are constrained to be less than the area of the sphere. Further, for the total interfacial area, we would add the area from the arc menisci or the corner areas and the throat areas. And we have used the bulk volume to normalize the area for per sample and represented it as total specific interfacial area with the units of millimeter inverse. This slide shows some of the results. The plot shows the connectivity of the non-wetting phase plotted as a function of the saturation of the non-wetting phase and color-coded by relative permeability. We can now rotate the figure to see that S, X, and A make a surface and that it can be color-coded with relative permeability, which also tells us that for a particular state function approach, if S, X, and A are all the same, the relative permeability will be a single valued function. Further, as we make it a versus S plot, we can see the primary drainage area, we can calculate the imbibition area and also the secondary drainage areas. As we start increasing the non-wetting saturation for the primary drainage, we observe that an increase in saturation increases the invading phase in the porous media and thus increases the interfacial area until it reaches to a saturation of 1, where it will again go back to the 0. The imbibition and secondary drainage curves follow similar trends. However, the imbibition has a much higher peak than the primary drainage due to the snapping off or trapping effect of the non-wetting phase. In this study, we have also calculated the throat areas or the MTMs and the corner areas or the arc menisci. Once we have all the data, now we want to see that whether saturation, connectivity, or interfacial area, which of the three parameters will affect the relative permeability most. For this, we use the out-of-bag predictor importance method, in which we input the whole data set of S, X, and A as predictors and relative permeability as the response for primary drainage, imbibition, and the secondary drainage curves. Once we input all the data, we use a random forest model to train decision trees. We have used 500 decision trees for this study. After the model is trained from all the data, what the out-of-bag predictor does is that it permutes every variable of the predictors such as saturation, connectivity, and interfacial area, and then figures out a response. Since it already knows what the true response is, it can figure out the error in the responses. And from those error, the higher the error in the predictors to the response is, the higher the estimate will be, and thus the higher the importance. The influence of a predictor increases with the importance, which is represented as this estimated number. So the takeaway from the slide is, for an estimator to be important, it has to have a higher estimate. The estimates for the predictor variables for saturation, connectivity, and area for the entire data set are presented here for the wetting phase and the non-wetting phase. We observe from the results that saturation is the most important parameter for the wetting phase, followed by connectivity and area. However, for the non-wetting phase, connectivity becomes the principal factor, followed by saturation and interfacial area. Physically, since the rock studied here is water wet, the wetting phase flows as the layers adjacent to the wall. Thus, the amount of the phase or the saturation controls the flow. However, for the non-wetting phase, connectivity plays a critical role due to the snapping off effect or the different trapping events during the imbibition and the reconnection of the isolated phases during the secondary drainage. More details about this workflow can be figured out in the citation as given here. We can also further zoom in each of these wetting phases and non-wetting phase data to analyze the sensitivity of the predictors across the saturation domain. In this slide, we look at the wetting phase, and the arrows point towards different quadrants that we have divided the saturation and connectivity domain in. We have used the three saturation domains. And as you can see from the results, in all of the domains, uh, the saturation dominates all quadrants over connectivity and specific area. In quadrant 2 particularly, the saturation is significantly more important than both connectivity and area. The high importance is likely due to the residual saturations in this region of the SX space, and thus at these residual zones, the phase saturation becomes the most important parameter. Similarly, for the non-wetting phase, we can also divide the SX space into four quadrants. We have particularly chosen the quadrants based on equal distribution of data points in all the three quadrants. And since the fourth quadrant doesn't have data, we don't analyze it. The results from the non-wetting phase indicate that connectivity is significantly important in all the quadrants, but specifically in the first quadrant, and again due to the presence of the residual saturations in the quadrant 1. Although specific area is not important as connectivity or saturation in the sensitivity results, it will still play an important role in the functional form of relative permeability. Such a qualitative analysis of the out-of-bag method is one of the drawbacks, however, it still gives us an idea of which parameter to focus on. Thus concluding that interfacial areas for primary drainage, imbibition, and secondary drainage is 0 at the limiting saturations of 0 and 1, and they peak in between. The relative permeability is most sensitive to saturation for the wetting phase and to phase connectivity for the non-wetting phase. And as stated, although area is not as important as the other two predictors, such as saturation and connectivity, it can still aid in the formulation of an accurate state function for relative permeability. These are the references used in this work, and that was it from my side. Thank you so much. I'm very thankful to the whole Porous Media team for giving me this opportunity, and I'm open to questions.
Thanks a lot, Sanchay, for your very nice work. I really appreciate how you apply machine learning techniques to this wettability saturation problem, and it's very interesting how to understand which parameters are more important than others, actually. And I believe this can be a really good application for the problem, for example, of carbon storage, but not only. I mean, in general, when you have to store, I guess, this CO2, and to understand how to make your system more also profitable in a way. Do you think that, so I have just a question, do you think that for the problem of CO2 storage, what can be the consequence of this work? Do you think that the CO2 storage should focus more in that particular phase diagram on the parameter that comes out to be the more relevant, or still have a mixture between the two in the proportional way according to your to what you've found?
Thank you. What we are trying to say here is that although we have multiple parameters here, but since we already looked at the sensitivities, so because we already always have very scarce data from the field, so given the opportunity to actually model for CO2 storage, uh, if we have to do it better than the Corey and the Brooks function, which are usually used in the industry, if we want to improve on that model, just maybe a parameter of connectivity might be added and it can improve the function significantly. So that's what we are trying to show, that maybe we don't want to complicate the interfacial area, but having that information gives us a little bit more insight in what's happening in that pore network.
Okay, makes sense. We have some questions from the audience. So one by Marcel. Hi, Marcel. Marcel says, "Very nice work. Congrats. Is the liquid in the corners static, or can you also have flow of the wetting phase in the corners?"
Thank you for the question, Marcel. So the liquid at the corners, it depends on the wettability of that particular state, what we are inputting. So for example, if it's completely water fed, it can the wetting phase can flow through the corners, while the non-wetting phase flows only in the centers of the pore elements.
We have another question by Susmit Chakraborty. Thanks, Sanchay, for the insightful talk. How do these phenomena vary from micro scale to macro scale? Do errors also vary with increase in scale? Thanks a lot.
Well, very interesting question. Thank you so much, Shushmit. So, of course, I would say that the phenomena may or may not vary from micro to macro scale. However, the errors will definitely vary. What we are looking at the micro scale, and once we go to the real field or the real data and look at the scale from a bigger perspective, definitely the errors, the manual errors or the system errors, the modeling errors, all this will combine in to give us more errors. How different it may or may not look, I am not sure about what will be the range of errors, but it will definitely be different. The trends might still be the same, but if you are looking at the numbers or, for example, exact values, they might definitely be different. Thank you.
Marcel, I think is another question related always to what you just answered about the angles in the pore geometry. Do you expect the conclusion to differ much if the pore geometry was not triangular?
So as I said, we considered the triangular element that I showed was just for an example. We have like a triangular element, a spherical element, as well as a cuboidal element in our pore network model. And for these particular pore elements, it will not vary because we consider it to flow. We consider the fluid to flow at the corners, so it's not static. For example, if it was a 180-degree wetting angle, then the non-wetting phase will take the sides of the wetting phase. However, in that case, because of the trapping or the layering effect, at that point, it might be trapped or the static effect can come into play, but not in this particular condition or the model that we have run in. That can be changed, and of course, the conclusions might differ if the wettability was different. I agree.
Okay. So there are other questions from the audience. You have still a few seconds to type eventually. In the studio, are there other questions?
I have a question of mine. It was extremely interesting results, and I thank you for that. Do you think when we are considering properties that are connected to fluid and also to the rock, for example, wettability and properties like that, how can we employ a similar technique and use it for different fluids, for example, in the context of petroleum industry, for CCS, or for hydrogen storage? How can we use the same technique and for complex parameters like wettability that has inputs from both surface and also fluids?
Thank you for the question, Mohammed. Actually, this work has impacts on both, as I said in the starting slide, that it can impact like the relative permeability because it exists in every multi-phase flow in the porous media in every application. So the impact of relative permeability will always be significant across multiple domains. Even, for example, if we had to do the same thing in gas EOR, we'll be looking at the relative permeabilities of oil and gas, or gas and water. And when we switch this to CO2 storage, we look at the relative permeabilities of CO2 and brine. So of course, this the significance of this work can be taken from different multiple domains, and they are not specific. But at the same point of time, the conclusions, as I said, the results may or may not be the same when we take it from one principle to another. The physics will still remain the same, the parameters will still behave the same, but the exact results may or may not remain the same. Thank you.
I believe so. If we don't have other questions, I believe that we can say a big thank to Sanchay.
Thank you
for his very good talk. And I believe we can move on with our second and last speaker for today. So say a warm welcome to Ashkan. Ashkan is a PhD student who obtained his bachelor degree in mechanical engineer from the University of Tehran in 2015. He then completed a master program at Amir Kabir University of Technology in Tehran in 2018, where he worked on nanostructural surface with specific wetting properties. And currently, his research focuses on understanding fluid displacement in mixed wet porous media. And today he will talk about, indeed, the characteristic of fluid displacement in mixed wet porous media. So, Ashkan, now it's your turn.
Thank you so much, Federico, for the introduction, and thank you for actually thank you to your team for the invitation. I'm just wondering, can you hear me properly and see my slides right now?
I can hear you perfectly and see your slide.
Great, thank you so much. And so, hello everyone. As Federico mentioned, I'm Ashkan, and I'm a last year PhD candidate at McMaster University under the supervision of Professor Benjang Zhao. Today we are going to talk about the characteristics of fluid displacement in mixed-wet porous media. And this work has been done in collaboration with Dr. Primakolov and Professor Ruben Juanes at MIT. But before jump into the details of the project, I just wanted to quickly talk about the fundamental concepts as well as the motivations behind this project. So you know that wettability is a measure of a liquid's affinity to a solid surface. So for example, at the picture at the left, water is wetting to this countertop, so it forms a film on that. But at the picture on the right, water is non-wetting to this umbrella and it builds up. Wettability is important in a wide range of applications, from geological carbon dioxide storage to contaminant remediation to enhance oil recovery. And wettability plays an important role in multi-phase flow in porous media, and we know it through decades of research, experimental and numerical research, and specifically this research, which has been done in 2016, which has used microfluidic flow cells with different wettability conditions, and it's showing us that as we increase the affinity of the porous medium to the invading fluid, the fluid displacement pattern becomes more compact. Recently, a novel pore network model introduced by Primakolov et al. That actually approximate the fluid displacement in porous media as current in an electrical circuit, and it is able to capture both viscose and wettability effects. So for the wettability effects, this model captures different types of pore scale invasion events, as was first proposed by Chepler and Robbins in 90s. And these three types of pore scale invasions include burst, touch, and overlap. Burst is equivalent to Haynes jumps, and touch happens when fluid-fluid interface that is connecting two grains meets the body of a third grains, and consequently it occupies the neighboring pore. And overlap happens actually when two adjacent fluid-fluid interface meet each other and join to each other to occupy the neighboring pore. So these pore network models and their very low computationally cost enable the researchers to perform a very systematic numerical study in which numerous simulations for different situations have been performed. And now we have a very good understanding of the fluid displacement process in porous media with uniform wettability. So the question is that, so what is the wettability of real natural porous media? What is the wettability of oil-bearer rocks or aquifer rocks? So the answer to this question has been easy in these years, thanks to advances in X-ray microtomography imaging techniques. And these techniques, these in situ wettability measurements, have shown that the distribution of wettabilities in natural porous media is especially heterogeneous. So in other words, natural porous media are not uniform wet, but they contain a wide range of contact angles. And natural porous media, in one sentence, natural porous media are actually mixed wet. So now here we are trying to understand what is the effect of mixed wettability on fluid displacement. And for that, we utilize microfluidic flow cells with spatially heterogeneous wettabilities. So we perform constant rates displacement experiments of ambient viscose silicone oil by water in microfluidic flow cells that consisted of more than 16,000 vertical cylindrical posts. And we fabricate these cells of a specific kind of polymer named NOID1. And these polymers' wettability can be tuned by exposure to high energy UV light. And we finally achieve to these flow cells, as we can see at this image, in which we have two different contact angles coexist. So for example, here, the gray posts have the contact angle of more than 90 degrees. They are oil wets. And these 4 blue clusters have actually the contact angle lower than 90 degrees, so they are water wet. So when we perform the experiments in these flow cells, where the contact angle of the oil wet area is 120 and the water wet area is 30 degrees, which means that the water wet clusters are strongly water wet, we see that the invading water preferentially fills the water wet cluster with the contact angle of 30 degrees. So this is what we expected to see, because intuitively we expected that. However, the surprising behavior is observed when we redo the test in a very similar mixed wet cell, but the only difference here is that the water wet clusters are just weakly water wet and their contact angles is 60 degrees. So in this case, we see that water preferentially invades the pore spaces that are bordering the oil wet and water wet regions. In other words, water prefers to enter to the mixed wet pore throats. To understand the role of these fluid-fluid interfaces at mixed wet pores, we quasi-statically study the evolution of fluid-fluid interface in mixed wet porous media using surface revolver, which works with minimizing the overall surface energy of the system. And we found out that the fluid-fluid interface that is bridging an oil wet post and the water wet post resemble a S-shaped saddle on which the total curvature is very close to 0. Next, we drive an analytical solution of fluid-fluid interface evolution through the mixed wet pore throat. And as we can see at the picture on the left, our analytical solution agrees well with the numerical prediction of surface revolver. And at the right, we are looking at one of our experimental observations that, as we can see, that specific S-shaped fluid-fluid interface inside our microfluidic flow cells and between 2 posts. At next step, we incorporate the capillary entry pressure associated with burst, touch, and overlap events in the mixed wet pores. And we incorporate these pressures into the pore network model that was developed with Promokolov et al. And finally, we reach pore network model that can capture the complexities of fluid-fluid displacement in mixed wet porous media. So here we are looking at the experiments, and the experimental results, and the numerical simulations that has been performed using these modified pore network model. So now that we have these dynamic pore network model that can accurately capture the properties of that, the next step is to use these use this framework to systematically investigate different kind of mixed wet cells and find and characterize the fluid-fluid displacement in porous media. So, however, until now, if you want to know more about the details of the experiments and the model, you can get access to this paper that is available right now on arXiv, and just recently was accepted to be published at Physical Review Fluids. And we have the link here. If you were interested, you can take a look at that. So we employ this pore network model to characterize the fluid-fluid displacement in mixed wet porous media. But the very first step to do that is to design different mixed wet cells with different mixed wettability states. So for that, we use a specific procedure in which we place base water wet clusters that the base water wet clusters have are similar. They have same size. The radius are 5 medium posts, and we randomly place them in the domain that is otherwise oil wet. So as a result, as a result of overlapping these base water wet clusters, we create complex mixed wet conditions in our cell. And a mix in our system, a mixed wet cell can be defined by A, the contact angle pairs, the oil wet and water wet contact angles, and B, the wettability fraction, which is the number of the water wet posts to the total number of the posts. Our systematic investigation includes more than 200 numerical simulations on a variety range of different mixed wet cells. We actually tested on 3 different contact angle pairs, 5 wettability fractions from 2% to 98%, and for a wide range of capillary number values from 5 times 10 to the power of -6 to 5 times 10 to the power of -4. And to verify the reproducibility of the results, we designed 3 different mixed wet cells with different water wet cluster placements for each wettability fraction. So here it is, the phase diagram of the invading fluid morphology at breakthrough. So here, each of these diagrams belongs to a specific contact angle pairs. So from left to right, the contact angle pairs are 30 and 120 degrees, 60 and 120 degrees, and 60 and 150 degrees. Each row is showing different capillary numbers. From top to bottom, the capillary number is decreasing, and each column is showing a specific wettability fraction from 2% water wet to 98% water wet systems. So just qualitatively looking at that, we see that at the top row, at the highest capillary number, the figures, the patterns actually look very similar to each other, which is due to the higher, the dominance of viscous forces at this case. But the most actual difference between the patterns is happening at the lowest row, where the capillary pressure is the lowest and the wettability is controlling the pattern. So to have a better understanding of this pattern, we use different quantitative metrics. One of them is, of course, the finger width of the patterns. And we can see that regardless of the contact angle, as we increase the wettability fraction, the finger width of the pattern increases. However, this increase is more significant in the mixed wet domains, in which the water wet cluster has the contact angle as low as 30 degrees, the one with strongly water wet clusters. And in this case, because of the predominance of overlap events, we have finger with higher widths. Another metric is fractal dimension, which characterizes the extent to which the displacement pattern fill the space in our 2-dimensional space. And we see here that although at low wettability fraction, increasing the wettability fraction leads to an increase in fractal dimension in both cases. At high wettability fractions, again, due to the difference between the intrinsic contact angle at the water wet cluster, we see that these 2 cases, these 30 and 120 and 60 and 120 degrees cases, exhibit opposite behavior. And finally, we track the evolution of injection pressure to gain further insight into the macroscopic impact of fluid-fluid displacement in mixed wet porous media. So specifically here, we are looking at the injection pressure evolution at 4 different cases with different wettability fractions. In all of them, the contact angles are constant, 120 and 30 degrees. And these simulations are done at low capillary number, when the capillary pressure is dominant and wettability controls the injection pressure. So if you look at the red line and the black line that are representing the oil wet system and water wet system, we can see that the injection pressure is more or less constant during the process, and it just very shortly fluctuates around a mean values that is positive for the oil wet system and negative for the water wet domain due to their capillary entry pressure. However, the most interesting behavior can be observed in the blue line, which belongs to the injection pressure in fluid displacement in a mixed wet cell with 20% wettability fraction, which means that just 20% of the pores and posts inside this cell is water wet and the rest are oil wet. So we see that we can see intense fluctuations in this case, and this is due to the sequential entrance of water to oil wet and water wet regions inside the cell. So whenever water oil interface is located at oil wet regions, we observe that the injection pressure actually increases to 150, which is more or less similar to the capillary entry pressure at drainage system. But whenever water enters to the water wet clusters, the injection pressure drops as we expected. But it is interesting that that the injection pressure is not dropped as low as the capillary entry pressure as at imbibition. And to understand this, actually understanding and explaining this distance actually help us to have a better understanding of what is happening at the pressure of this system. So here we are looking at a pressure map inside the cell when the water is entering to a water wet cluster. We see that in this case, all the injection volume at this time step will preferentially enter that small region of the macromodel, the water wet region. So, and because the water wet clusters are small at low wettability fractions, the preferential filling within this localized region will cause the defending fluid to redistribute along the fluid invasion front. And as a result, we can see that the flow rate, the local flow rate at that region is maximized, while the flow rates at other throats are almost zero. And that's relatively high flow rate at the water wet cluster leads to higher pressure loss, viscous pressure loss. So we can say that at mixed wet systems, even at very low capillary number, viscous pressure loss is not negligible. And with that, we reach the conclusions. So overall, we investigated the impact of mixed wettability in viscosely unstable two-phase flow via experiments in macrofluidic flow cells. We developed a pore model that is able to capture the complexities of the process. And finally, we employ the dynamic pore network model to characterize the displacement in mixed wet porous media based on the patterns and pressure. Thank you so much for your time and your consideration. I would be happy to take the questions.
It seems that we cannot hear you, Mahdi.
Still now.
Now we can hear you.
Can you hear me now?
Yes.
Yes.
Okay, great. Thank you very much, Ashkan, for the great talk. Beautiful results. I personally have a couple of questions. According to your slides number 8 to 10, what do you think is the role of precursor film in the difference between the case that you have 60-degree contact angle and 30-degree contact angle? And have you considered to take them into account for your pore network models or any other modeling in the future?
Mm-hmm. Actually, that's a very, very good question. No, actually, we have not included that into our model yet. However, it is an ongoing project, and we will actually consider that in the next steps, because you're right that would be a very interesting and make it more make it more make the model actually even more realistic. And yeah, but here, no, we are not considering that, and we cannot see that actually in our we don't have it actually in our experimentals as well.
All right. Okay, thank you. So questions from the audience. Gigi, I hope I'm pronouncing right. Gigi Giretto asks, what is the difference between the circuit model you mentioned and the standard Power network model, where the Poiseuille law can be already seen as the equivalent to Ohm law?
Yeah, that's a very good question, actually. It is, right now, I'm going to talk about that briefly. But for more details, I highly actually encourage you to take a look at this paper by Primikov et al. So overall, we can say that in this model, the viscous drop across the pore throats can be considered and can be actually approximate with currents in resistors. And so the out-of-plane curvature of the fluid-fluid interface is can be approximate with the current in batteries, as you can see here. And the in-plane fluid-fluid interface that is changing, and it needs to reach to a specific amounts to which is the capillary interpressure to the neighboring port to be occupied, is approximated as currents in a capacitor. So yeah, this is the overall how the system works. But still, to be more to read about it in more details, I think this paper with Primikov et al. Would be very beneficial.
Okay, great. Ehsan thanks you for the interesting talk and asks, I'm wondering how rough is the surface in your microfluidic flow cell? Is the roughness similar to in the water wet and oil wet regions?
Thank you. Yeah, that's a very good question. In our case, actually, as I said, our microfluidic flow cells are made of a specific kind of polymer, no ID1. So the technique that we use give us a very smooth surfaces, and the roughness are as small as a few nanometers. And the roughness is more or less similar at both water wet regions and oil wet regions, and it's very important. Again, I want to refer you to another paper here, written by Masumini et al. That has been actually, for more details about the chemical characteristics of this kind of microfluidic cells with different control wettability situations and the roughnesses, I think this would be a very beneficial paper to read and understand all details of that. But yeah, overall, the system is very smooth, and the roughnesses are as small as a few nanometers, both at water wet and oil wet systems.
Okay, great. Marcel here, wonderful talk. Congratulations to the brave researchers that dare to play with the wettability. This is hard. Could you comment on what was, in your opinion, the most challenging step for the experiments?
Thank you, Marcel. Thank you so much. So the most challenging step in the experiments was aligning two different actually parts of the cell. So so here, as you can see, we didn't want to have just water wet and oil wet posts side by side, but we also wanted to have mixed wettability on our bottom and top surfaces. So the most challenging part was to aligning these two surfaces perfectly to each other, and to make sure that we have a perfect mixed wet pore throat. And to do that, we had to actually create a setup with different microscopes and alignments tools to be able to to do that really accurately. And yeah, I think that was the most challenging part of this experiment. And of course, another one was that each cell, it takes a few days to be prepared, and it's polymer. It was really sensitive, and we just were able to use a cell just for one experiment. So yeah, it was all the process have to be done actually correctly. So it was just all or none. So yeah, that was the experimental parts actually was very challenging. And yeah, I think that is the most challenging one.
Okay, great. Do anyone from the studio have any question?
Yeah, sure. I can ask one. Thank you, Ashkan, for the great presentation. I wanted to ask, when you were comparing the pore network model and the experimental results, they quite seem to be very good, like similarity between them. So I wonder, like, what type of pore network model are you using? Like, is it static, or like what is the structure of the pores and throats? Is it like full volume, or does it not have volume? Some details on that. Thank you.
Oh yeah, for sure. So let me just go back to this slide again. Yeah. So the core of this actually the model that we have used is the Primikolov's model, whose details are brought at this paper. And yeah, it is a dynamic model. It captures the viscous pressure drop using actually Poisson law. And also, these are how the geometry actually looks like. So we have actually a cylindrical post, so more than 16,000 cylindrical posts, and the top and bottom surfaces are just flat. And also, we capture the wettability, the different pore scale invasion events, burst, touch, and overlap. These three inside that, and for both water wet posts and pores, actually oil wet pores and the mixed wet pores. And yeah, that is how it works. If you have any specific question, I would be happy to answer. Or actually, again, I suggest to take a look at this very fantastic paper by Bayjan, 2019, and JFM. And it will give you very good information about this interesting model.
Thank you.
Okay. Thank you, Ashkan. Personally, I have one more question. It's more technical question. How do you exactly define, because you answered to some extent, like how do you exactly define like what regions to be wet, like water wet, and like to have 30 degrees contact angle? Do you use like photomask in like clean room facilities, or you have another method for that?
No, as you said, we use actually different type of masks. So overall, these surfaces and this polymer is its wettability can be tuned by being exposed to high energy UV light. So if you put it inside the UV ozone cleaner machine, when it is exposed to UV lights, the chemical composition of the surface will be changed, and it becomes the surface becomes more water wet. So to make sure that, so we wanted to have some parts water wet and some others oil wet. So the parts that we wanted to remain oil wet, we blocked them. We blocked those areas inside the clean room, of course, using a UV blocking mask, and then we expose it to high energy UV light. So the areas that receive actually that's UV light, they became water wet, and the regions that are blocked remain oil wet. And so again, more details about different techniques to create special to create 2D or 3D microfluidics with special wettability conditions are brought here in this paper. And yeah, I highly recommend to, if you're interested in these techniques, take a look at this paper. There are very good stuff there.
Okay, great. Thank you very much.
Thank you.
No more questions. Let's thank Ashkan again for the great talk.
Thanks.
Okay. So it was officially the last Porous Media Tea Time Talk session for the 2022. And thank everyone that throughout the 2022 year have been here, and thank for the audience that have been attending our seminars. This is us, the Porous Media Tea Time Talk, Porous Media Tea Time Talk managers. Thank you very much again for each person that attending our talk, and I hope you have a very happy New Year and wish you very beautiful vacations throughout the New Year vacations. And that would be it. Let's close the session. Thanks everyone again. Bye.